Okay, in this video we're going to be doing Calc AB Problem Set 20. A link to the problems and a playlist of all the problem sets is down below. And let's get started. So we have a table. The function f is twice differentiable and values are shown in the table above. Okay, we want to approximate f prime of 7. I see people kind of struggle with this sometimes. There's like not much to do here. You look at the table and you find the number to the left of 7, the number to the right of 7, and you just use the secant slope between them. Like there's nothing more to that. So I'm going to say that f prime of 7 is approximately, because it's not definitely equal to this, it's approximately equal to, so I'm going to do f of 9 minus f of 5 over 9 minus 5, and then calculate it, I get negative 3/4. There you go. That question shows up on the AP exam free response like almost every year, so make sure you know how to do that. All right, we want to prove that f prime is equal to 0 for some x between 0 and 5. So we look at the table. There are no y values that are the same between 0 and 5. So now you have to start thinking, like, between 0 and 4, the y values increase. So we could show that f prime is positive there somehow using mean value theorem. And then between 4 and 5, the y values decrease. So we could show that f prime is negative there using the mean value theorem, and then f prime will have gone from positive to negative. If we can show that f prime is continuous, IVT will guarantee us that f prime is equal to 0. So that's what I'm going to try to do. So here goes. F of x is twice differentiable, therefore f of x is continuous. You might want to say therefore f of x is differentiable and continuous, but like twice differentiable means differentiable, so it's basically given that f of x is differentiable. And then we have to infer that it is continuous. But that means that we can use mean value theorem on f of x. So we're going to apply the mean value theorem to f of x to conclude something about f prime. So I will say f prime of c1, because I'm going to do it twice and I already know that, so I'm setting that up. F prime of c1 is f of 4 minus f of 0 over 4 minus 0, which gives us, it gives you 2 over 4, but 1/2, which is greater than 0. For some c1 between 0 and 4, so that's by the mean value theorem. We're going to do it again between 4 and 5. F prime of c2 is f of 5 minus f of 4 over 5 minus 4. That gives us negative 1, which is less than 0 for some c2 between 4 and 5. Okay, so we now know that f prime is positive somewhere and then negative somewhere else. So now we're going to try to use the intermediate value theorem. So to use the intermediate value theorem, I need f prime to be continuous. I know that f prime is continuous because f is twice differentiable. So f is twice differentiable, which means f prime is differentiable, and if f prime is differentiable, it is continuous. Okay, so now we know that f prime is continuous. We can use IVT on it. So I'm going to say f prime of c2 is less than 0, which is less than f prime of c1. Therefore, by IVT, f prime of x equals 0, for some x between 0 and 5. And we did it. All right, the next question is, obviously I'm going to need another page. Prove f double prime is equal to 0 for some x between 0 and 12. All right, so let's think this through. Like, we already know that f prime is equal to 0 somewhere. If I can find another place that f prime is equal to 0, then I can just use the secant line to f prime has a slope of 0, which means that f double prime must be 0 by a mean value theorem. That's my goal. Looking at the table, so we know already, right, from part B, I'm going to say f prime of d1, so I'm like renaming it, but I think that's cool. F prime of d1 is equal to 0 for some d1 between 0 and 5. That's from part B. That's basically what we proved there. So looking at the table, we have between 5 and 12, because 0 to 5 we already know what happens. Between 5 and 12, at 5 and 12, you have a y value of 4. So I'm going to use the mean value theorem there to conclude something about f prime. So here goes. Since f is twice differentiable, f is differentiable, and therefore continuous. So I repeat a lot of things. I try to do each section as if I didn't do a previous one. I know that's completely a lie because the first thing I wrote was from part B. But I'm redefining everything. I'm just restating things so that someone can read this and be like, I understand. So f is twice differentiable, f is differentiable, f is continuous. So the mean value theorem applies. So I'm going to say that f prime of d2 is f of 12 minus f of 5 over 12 minus 5. That gives us 0 because they both have a y value of 4. for some d2 between 5 and 12, and that's by the mean value theorem, because we always want to say what we're using to like draw these conclusions. Now we know that f prime of d1 is 0, f prime of d2 is equal to 0. We now want to apply the mean value theorem to f prime to conclude something about f double prime. So it's like mean value theorem always goes down a level. It's like you use it on f to tell you something about f prime, you use it on f prime to tell you something about f double prime. You could use it on f triple prime to tell you something about f the fourth derivative. I don't want to like quadruple prime. All right, so if I'm going to use the mean value theorem on f prime, I need f prime to be continuous on the closed interval, differentiable on the open interval. So we know that's true though, because f is twice differentiable, which means f prime is differentiable and therefore continuous. So we can use the mean value theorem. So I'm going to finish this off by saying, therefore, by mean value theorem, f double prime of x is equal to f prime of d2 minus f prime of d1 over d2 minus d1, which we know is equal to 0 because f prime of d2 is 0, f prime of d1 is 0. So we did it, I think. So for some x between 0 and 12, this is a really important like work through. I think this problem set is really good to review. Like if you've did it successfully, good. If not, like maybe watch this again. Try to internalize these ideas, because you do a lot of this kind of like reasoning about a table and applying either intermediate value theorem or mean value theorem to a table a lot. Anyway, this problem set's done. Hope this was helpful, and good luck.